The universe holds secrets that defy everything we think we know. You will discover 23 phenomena that still baffle astrophysicists, taking you to the very edge of cosmic understanding. These are not minor gaps in knowledge, but profound mysteries shaking the foundations of physics itself. We will explore why most of the universe's matter is completely invisible and what force is ripping space apart at an ever-increasing rate. By the end, you will see the cosmos through the eyes of a scientist confronting its greatest puzzles. What do you believe is waiting to be discovered in the dark? The cosmos is hiding something from us. Picture every star, every planet, and every swirling nebula you have ever seen in a telescope. All of it, every last bit of visible matter, accounts for less than 15% of the actual substance holding the universe together. The rest is a ghost, an invisible presence known as dark matter, whose gravitational grip is the only thing preventing galaxies from flying apart. This is not a small adjustment to our theories. It is a fundamental crisis in our understanding of reality. The first solid clues emerged from the work of astronomer Vera Rubin. She meticulously mapped the rotation of galaxies, expecting to find that stars on the outer edges, farther from the galactic core, would move slower, just as Pluto orbits the Sun more sluggishly than Mercury. But the data told a different story. Stars at the very outskirts of galaxies were racing around just as fast as those near the center. It was as if the entire galaxy was embedded in a massive, unseen halo of matter, providing extra gravitational pull. The visible galaxy was just the bright tip of a vast, dark iceberg. We cannot see dark matter because it does not interact with light. It does not emit, absorb, or reflect it. We only know it is there because of its gravitational effects, which act like a cosmic signature. One of the most dramatic pieces of evidence comes from a violent cosmic collision known as the bullet cluster. When two galaxy clusters smashed into each other, their hot, visible gas slowed down and piled up in the middle. But something else, the majority of the mass, kept right on going, detected only by how its gravity warped the light from galaxies behind it. This proved that dark matter can be physically separated from normal matter, a clear sign it is a real, physical substance. So what is it made of? For decades, the prime suspects have been theoretical particles with names straight from a physicist's imagination. Weakly interacting massive particles, or WIMP, are heavy particles that barely interact with normal matter. Another candidate is the action, a particle so lightweight and elusive it could be streaming through you by the trillions every second without you noticing. Yet despite incredibly sensitive experiments deep underground, like the LUX and Xenon projects, which wait for the faintest bump of a dark matter particle, nothing has been conclusively found. The silence is deafening. This leaves us with a profound question. What if dark matter is not just one missing particle, but a sign of an entire hidden sector of physics? A whole new set of rules and particles operating just beyond our perception. This invisible architecture, the very scaffolding upon which galaxies are built, has a partner in mystery, a force that works against it on the grandest scales. This invisible force has a cosmic counterpart, a push that counteracts gravity's relentless pull. While dark matter works to bind the universe together, something far stranger is working to tear it apart. The very fabric of space is not just expanding, it is accelerating, with galaxies fleeing from one another at a pace that grows faster every single moment. This discovery was so shocking it earned the Nobel Prize. In the late 1990s, two independent teams of astronomers were observing distant stellar explosions, a special type of supernova that acts as a standard candle for measuring cosmic distances. They expected to find the expansion of the universe was slowing down, gradually decelerating under the collective gravity of all its matter. Instead, their data revealed the opposite. The most distant supernovae were fainter than they should have been, meaning they were farther away than anyone had predicted. The universe's expansion was not slowing, it was speeding up. This was like tossing a ball into the air and watching it not only fail to fall back down, but shoot away from you into the sky at an ever-increasing velocity. The force responsible for this bizarre behavior was named dark energy. It constitutes a staggering 68% of the universe's total energy density, the dominant component of reality, and we have no idea what it actually is. Nobel laureate Saul Perlmutter described the finding as learning the universe has been keeping a secret from us. This secret rewrites our cosmic destiny, pointing towards a future where galaxies become so isolated they are lost from view, leading to a cold, dark, and lonely end. One of the oldest theoretical explanations comes directly from Albert Einstein's own equations. He included a fudge factor called the cosmological constant, a repulsive energy inherent to the vacuum of space itself. When he learned the universe was indeed expanding, he reportedly called it his greatest blunder, but he may have been right for the wrong reason. The problem is one of scale. When physicists calculate how much energy this vacuum should contain, the theoretical value is wrong by a factor of 1 followed by 120 zeros. It is the worst prediction in the entire history of physics. Other theories propose a dynamic force field, given the name quintessence, which could change over time. Or perhaps Einstein's theory of general relativity itself breaks down on the largest scales and needs to be modified. Projects like the Dark Energy Survey are now mapping millions of galaxies to measure the expansion history with unprecedented precision, hoping to find a clue in the subtle patterns of the cosmic web. Could this mysterious push grow so strong that it eventually overwhelms all other forces? This leads to a terrifying possibility known as the Big Rip, a hypothetical end to the universe where dark energy becomes so dominant that it tears apart galaxies, then solar systems, then planets, and finally the very atoms that compose all matter. As we contemplate this accelerating fate for the cosmos, we are forced to confront a fundamental puzzle about its very beginning. Our very existence hinges on a cosmic oversight. According to our best theories, the Big Bang should have created matter and antimatter in perfectly equal amounts. For every electron, there should have been a positron, its antimatter twin. For every quark and antiquark, when a particle meets its antiparticle, they annihilate each other in a flash of pure energy. If the universe had begun with perfect symmetry, all of its contents should have mutually destroyed themselves, leaving behind a vast, empty sea of radiation. There would be no stars, no planets, and no one to wonder why. Yet here we are. Somehow, for every billion pairs of matter and antimatter that annihilated in the early universe, one single particle of matter was left over. That tiny 1 in a billion imbalance is everything we see, everything we are. The Russian physicist Andrei Sakharov outlined the 3 conditions needed for this to happen. One of the most crucial is a phenomenon called CP violation. This is a subtle breaking of symmetry in the laws of physics, where a particle and its antiparticle do not behave as perfect mirror images. We have observed this in the decay of certain exotic particles like kaons and B mesons, in giant particle accelerators like the one at CERN. But here is the baffling part. The amount of CP violation we have measured is far too small to account for the overwhelming dominance of matter we see in the cosmos. It is like finding a single drop of water in a desert and being told it caused a flood. So where did the rest of the asymmetry come from? Experiments at detectors like LHCb at CERN are hunting for new, stronger sources of this symmetry breaking, searching for any particle that decays in a slightly lopsided way. Theorists have proposed entire new realms of physics to explain it. Perhaps supersymmetry, which predicts a heavy partner for every known particle, could provide the answer. Maybe ghostly neutrinos, which oscillate between different types, are their own antiparticles and hold the key. Or could primordial black holes, formed in the first instance of time, have somehow tipped the scales? The question is as profound as any can be. Why does the universe, which seems to value balance and symmetry in its fundamental laws, exhibit such a blatant preference for matter? This foundational puzzle about the stuff we are made of forces us to look back even further, to the very first fraction of a second when the cosmos was born. That 1 in a billion surplus of matter was forged in a universe of impossible smoothness. Look in any direction, and the afterglow of the Big Bang appears remarkably even. The cosmic microwave background radiation, a snapshot of the infant cosmos, shows a temperature that is uniform to an astonishing degree, varying by less than 1 part in 100,000. This presents a problem of cosmic communication. How can regions on opposite sides of the observable universe, so distant that light has not had time to travel between them since the beginning, share the exact same temperature? They should be like two strangers in separate, isolated rooms who have never met, yet they are both wearing identical outfits down to the last thread. Without a way to exchange information, this perfect thermal equilibrium should be impossible. This is the horizon problem, a deep puzzle about causality and the universe's initial conditions. The leading solution is a breathtaking idea called cosmic inflation. It proposes that in the first tiny fraction of a second, the universe underwent a growth spurt of unimaginable ferocity, expanding exponentially faster than the speed of light. This does not violate relativity because space itself was stretching. A single, minuscule patch that had time to even out its temperature was suddenly inflated to become larger than our entire observable universe. This process stretched any initial wrinkles flat, explaining the profound smoothness we detect today. But what powered this incredible burst? Theorists propose a mysterious field, dubbed the Inflaton field, whose energy drove the rapid expansion. Then, just as suddenly, this field decayed, dumping its energy to create the hot soup of particles for the conventional Big Bang. The mechanism remains deeply speculative. Was it a quantum fluctuation, a phase transition, or something else entirely that flipped the switch? To find answers, scientists are searching for the ripples such an event would have left in spacetime itself. Collaborations like BICEP at the South Pole scan the faint polarization patterns in the cosmic microwave background, hunting for the faint imprint of primordial gravitational waves, the tremors from inflation's first moment. Finding them would be a smoking gun, yet for a theory that explains such perfect smoothness, it leaves us with a profound contradiction. Why, if the early universe was stretched so perfectly flat, is our cosmos today so beautifully lumpy, filled with the galaxies and voids that form the cosmic web? That beautiful lumpiness, the cosmic web of galaxies, began with the most subtle of seeds, yet the very process that forged the first atoms of the universe left behind a stubborn, elemental mystery. Our mathematical models of the Big Bang are exquisitely precise, capable of predicting the amounts of the lightest elements forged in that first fiery furnace. For helium and deuterium, the predictions match the observations in ancient gas clouds and old stars with stunning accuracy. It is a triumphant confirmation of our cosmic origin story. But for one element, the numbers are catastrophically wrong. Lithium, the third lightest element, appears in the oldest stars of our galaxy, at only about 1/3 the abundance our theories demand. This is not a small rounding error. It is a fundamental gap in our understanding of the universe's first few minutes. The lithium problem was first spotted decades ago when astronomers measured the atmospheres of ancient stars, time capsules that preserve the pristine chemical composition of the early cosmos. No matter how they looked, the amount of lithium-7, the main isotope produced by the Big Bang, was always far too low. It is as if a master chef followed a perfect recipe, but one key ingredient consistently refused to appear in the promised amount. So where did the lithium go, or was it never made in the quantities we think? Perhaps our understanding of the nuclear physics itself is flawed. The primordial soup was a frenetic dance of protons and neutrons, colliding and fusing in a rapidly cooling universe. The exact probabilities, known as nuclear cross-sections, for these reactions are measured in sophisticated particle accelerators. Even a tiny miscalculation in one of these rates could cascade through the entire chain of nucleosynthesis, potentially resolving the discrepancy. Teams are constantly refining these measurements, but so far, no adjustment has fully closed the gap. Could something more exotic be at work? Some theorists propose that previously unknown particles, like certain types of supersymmetric particles, were present in those early moments. Their subsequent decay could have altered the delicate balance of nuclear reactions, essentially destroying lithium as it formed. Others wonder if the ancient stars we use as cosmic laboratories are not as pristine as we assume. Perhaps over billions of years, these stars have somehow dragged lithium down from their surfaces into their deeper, unobservable interiors, hiding the evidence from our telescopes. The lithium problem is a quiet but persistent thorn in the side of cosmology. It reminds us that for all the grand success of the Big Bang model, a complete picture of our origins still eludes us. Solving it might not require a revolution, but it demands a perfection of our tools and a willingness to question even our most solid-looking assumptions. What other subtle clues about the infant universe are we misreading as we stare into the stars? This puzzle of a missing element shifts our gaze from the vast expanse of the cosmos to the strange behavior of the very particles that constitute it. Even the most carefully measured cosmic distances are now telling us two different stories. The universe's expansion rate, a fundamental number known as the Hubble constant, is at the center of a growing crisis. On one side, we have the view from the ancient universe. The Planck satellite meticulously mapped the faint afterglow of the Big Bang, the cosmic microwave background. By analyzing the subtle ripples in this primordial light, scientists can calculate how fast the cosmos should be expanding today. This method gives a precise value of about 67 kilometers per second for every megaparsec of distance. Think of a megaparsec as an immense cosmic ruler over 3 million light-years long. This result suggests that for each additional megaparsec you look out into space, galaxies are receding from us 67 kilometers per second faster. But then we look at the modern universe. Astronomers like Nobel laureate Adam Rees use cosmic lighthouses, pulsating stars called Cepheid variables, and brilliant supernova to directly measure distances and velocities to relatively nearby galaxies. This painstaking step-by-step measurement yields a different answer, around 73 kilometers per second per megaparsec. The universe appears to be expanding significantly faster now than the ancient light says it should be. This discrepancy is known as the Hubble tension. The true puzzle is that as our tools have become sharper and our measurements more precise, the gap between these two values has not shrunk. It has grown more significant and stubborn. It is as if you used two different, perfectly calibrated rulers to measure the same table and got two consistently different answers. One of our most trusted cosmic rules appears to be broken. Rees has called this the most exciting thing in cosmology today. because this persistent tension is a powerful hint that we might be missing a crucial piece of physics. Perhaps dark energy is not a constant force but has been evolving over time, growing stronger and pushing the universe apart faster than anticipated. Another proposal is an exotic form of early dark energy, a temporary repulsive force that existed for a brief moment in the universe's infancy, subtly altering the initial conditions that the Planck satellite measures. Or maybe we need to reconsider the properties of ghostly neutrinos, which could have more mass or interact in stranger ways than we currently understand, affecting the cosmic growth rate. The most radical possibility is that our theory of gravity, Einstein's general relativity, while brilliant, is subtly incomplete on the scale of the entire cosmos. New observations from powerful observatories like the James Webb Space Telescope are now zeroing in on this problem, scrutinizing the Cepheid stars and supernova with unparalleled clarity to eliminate any potential for hidden measurement errors. The Nancy Grace Roman Space Telescope will soon join this effort, mapping the cosmos in immense detail. Either we will find a subtle flaw in our techniques, or we will be forced to accept that the universe is governed by laws we have not yet discovered. This fundamental conflict over how fast everything is moving apart makes us question the very nature of the space through which it all travels. Even the most ancient light in the universe seems to hold a personal grudge. The cosmic microwave background, that pristine remnant from the dawn of time, is not as perfectly random as our theories demand. Its subtle temperature fluctuations, the seeds of all future galaxies, appear to whisper a secret alignment with our own small corner of the cosmos. This bizarre correlation, so unsettling that scientists nicknamed it the axis of evil, suggests the entire universe might have a preferred direction, one that eerily matches the plane of our solar system. It is as if the grandest map of creation has a faint watermark that reads, "You are here." This discovery, first spotted in data from the WMAP satellite and later confirmed by the more precise Planck mission, strikes directly at the heart of a foundational belief in cosmology. The cosmological principle states that the universe on large scales should look the same in every direction. It should be isotropic with no special place and no preferred axis. The axis of evil is a ghost in the machine that seems to violate this core tenet. The anomaly appears in the way the light is organized, specifically in its low multipole moments. Think of the universe's background hum not as a single note but as a chord. The quadrupole and octupole, the very first overtones in that chord, are not ringing out randomly. Their patterns of hot and cold spots show a strange preference, a statistical alignment that points back toward our own ecliptic plane. The probability of this happening by pure chance is incredibly low. So what are we seeing? The most conservative explanation is that we are fooling ourselves. Perhaps there is a subtle, undiscovered systematic error in how we process the data from these magnificent telescopes. Maybe the way our solar system moves through the galaxy, or even interstellar dust, is contaminating the signal, imprinting a local signature onto a global map. But if it is not an error, the implications are staggering. Could it be evidence of a pre-Big Bang structure, some imprint from a previous cosmic phase that set a preferred orientation for our entire universe? Or does it hint at the shape of the cosmos itself, a complex topology where space wraps around in a way that creates these strange correlations? The axis of evil remains one of cosmology's most persistent and embarrassing puzzles. It forces us to ask an uncomfortable question. Are we truly seeing the universe as it is, or are we merely seeing the reflection of our own place within it? This large-scale oddity finds a strange echo in the behavior of individual cosmic giants, whose own motions defy simple explanation. Our own galaxy is racing through the void at an astonishing speed. The Milky Way is not drifting aimlessly, it is being pulled, dragged at over 600 kilometers per second toward a specific point in the depths of space, toward the constellation Centaurus. The force required for this immense tug-of-war must be colossal, but when we look in that direction, we see only a partial answer. There lies the Great Attractor, a gravitational anomaly of almost unimaginable scale, a concentration of mass equal to tens of thousands of galaxies all clumped together. Yet a huge portion of this behemoth is hidden from our direct view, obscured by the thick dust and stars of our own galaxy's central bulge, a region astronomers call the zone of avoidance. For decades, this was a ghost in our cosmic maps, a shadow detected only by its pull. The first clues emerged in the 1970s, when astronomers noticed that entire galaxies, including our own, were not simply moving with the universe's general expansion. They had a peculiar velocity, a specific motion, all pointed toward this one mysterious spot. It was like feeling a constant, powerful wind, but being unable to see what was causing it. What could possibly possess enough gravity to command the motion of our entire galactic neighborhood? We have since managed to peer a little deeper using telescopes that see in infrared and radio waves, which can penetrate the cosmic dust. These observations revealed some of the structure, including a massive galaxy cluster known as the Norma cluster, which acts as the heart of the Great Attractor. But even this vast assembly of galaxies does not seem to account for the full strength of the gravitational pull we feel. The mystery deepens when we look beyond it. Lying even farther in the same direction is the Shapley supercluster, the most massive known concentration of matter in our observable universe. It is also pulling us, adding its own immense gravity to the mix. So our motion is a cosmic tug-of-war between these two giants, the Great Attractor and the Shapley supercluster. This raises a profound question. Is the Great Attractor a distinct structure, or is it merely a stepping stone, a local overdensity on the filamentary web that leads to the even greater mass of Shapley? What other colossal assemblies of galaxies and dark matter remain hidden behind the veil of our own Milky Way, forever invisible to our optical telescopes? The Great Attractor teaches us that we are not merely observers of the cosmos. We are participants in its vast dynamic flows, caught in a river of gravity whose true source we have only begun to map. Our entire galactic neighborhood floats in a cosmic desert of staggering proportions. This is the Keenan-Barger-Cowie void, a region of space so vast it defies easy comprehension, spanning over 2 billion light-years across. Within this immense volume, the density of galaxies is about 20% lower than the average for the observable universe. We are not living in a typical part of the cosmos, but in one of its grandest underdensities. The discovery emerged from meticulous galaxy surveys, where astronomers like Ryan Keenan and his colleagues mapped the three-dimensional distribution of millions of galaxies. They found our local group of galaxies, including the Milky Way and Andromeda, sitting squarely in the center of this colossal bubble of relative emptiness. This placement directly challenges the cosmological principle, the long-held assumption that on sufficiently large scales, the universe is smooth and homogeneous with no special places. A void of this scale should be exceedingly rare, if not impossible, within our standard model of cosmology. Its sheer size brushes up against the theoretical maximum predicted by cosmic inflation, the process that is thought to have smoothed out the early universe. How could such a gigantic fluctuation survive that smoothing process? The existence of the KBC void forces a difficult choice. Either we are the beneficiaries of a 1 in a billion statistical fluke, living in an anomalously empty part of the cosmos, or our understanding of how cosmic structures form from the primordial seeds of inflation is fundamentally incomplete. Some cosmologists have proposed that such a giant void could be explained by more complex models of inflation, where quantum fluctuations created rare, ultra-large underdensities. Others have analyzed different galaxy catalogs to check the void's significance, with some studies confirming the underdensity and others suggesting it might be less pronounced. The implications reach even further. Could our position inside this cosmic emptiness be skewing our measurements of the universe? When we look out from inside a void, the local geometry and expansion rate are subtly different than in the average, dense universe. This perspective might be affecting how we calculate fundamental numbers like the Hubble constant, potentially contributing to the troubling tension between different measurement methods. It is a profound reminder that we are not just observers of the cosmos, but active participants within its structure, and our local environment may color our view of the whole. As we contemplate our place in this grand emptiness, our attention is drawn to the strange, solitary giants that sometimes wander into it from the dense cosmic web beyond. Sometimes the greatest mysteries are not found in the distant cosmos, but in the quiet drift of our own robotic explorers. For decades, as the Pioneer 10 and Pioneer 11 spacecraft journeyed beyond the planets, they carried a secret. A tiny, persistent push was subtly altering their paths. Through painstaking analysis of their radio signals, a faint Doppler shift revealed an unexplained acceleration, a constant sunward tug of about 8.74 times 10 to the negative 10 meters per second squared. It was a whisper of a force so small it should have been negligible, yet it was there year after year across billions of miles of empty space. This was the Pioneer Anomaly, a navigational ghost that refused to fade away. For a time, it seemed we might be on the verge of a revolution in physics. Could this be evidence of modified gravity, a crack in the flawless edifice of Einstein's general relativity? Perhaps it was a sign of dark matter exerting a local pull within our solar system. The possibilities ignited the imaginations of theorists, suggesting our understanding of the fundamental forces was incomplete. But science has a way of demanding mundane answers for seemingly magical problems. The most likely culprit turned out to be the spacecraft themselves. These probes were powered by radioactive thermoelectric generators, which produced heat as they decayed. That heat had to go somewhere. A meticulous, years-long effort to model the spacecraft's thermal properties revealed that photons, particles of light carrying thermal radiation, were leaking from the warm side of the craft in a slightly uneven way. This anisotropic radiation acted like a gentle, continuous photon thrust, providing just enough push to account for most of the anomalous acceleration. The case was largely closed, with the scientific consensus settling on this thermal explanation. Yet, a sliver of doubt remains for some, a tiny residual anomaly that the thermal models cannot perfectly explain. This entire episode is a masterclass in scientific detective work. It shows that even the most tantalizing hints of new physics can sometimes be traced back to the complex, real-world behavior of our own machinery. It proves that our measurements have become so exquisitely precise that we can now detect the faint pressure of light itself pushing against a spacecraft. As we send new probes into the darkness, like the New Horizons mission now traveling through the Kuiper belt, we must ask what other minute, almost imperceptible drifts they might experience. What other subtle forces hidden in the noise of our instruments are waiting to be discovered? This puzzle of a gentle, unexpected push finds a strange parallel in the violent, chaotic dance of the early solar system. Even our most precisely planned space missions can carry home a tiny, unsolved puzzle. The Flyby anomaly is a ghost in the machine of orbital mechanics, a minuscule but persistent shift in velocity that defies our best predictions. When a spacecraft swings past Earth to use our planet's gravity as a slingshot, engineers can calculate its trajectory down to the millimeter. Yet on several occasions, as these probes raced away, ultra-precise Doppler tracking revealed a discrepancy. Their speed had changed by a few millimeters per second, a deviation so small it sounds trivial, but in the unforgiving realm of celestial navigation, it is a glaring inconsistency. The first documented case was NASA Galileo spacecraft in 1990. As it departed Earth on its long journey to Jupiter, it gained a tiny, unexpected boost in velocity. This was not a one-time fluke. The same mysterious nudge was later measured with the near-Shoemaker spacecraft headed to an asteroid, the Rosetta probe on its way to a comet, and even the Juno mission to Jupiter. Each time, the anomaly was on the same order of magnitude, a whisper of extra speed that our models of gravity and motion could not account for. The pattern that emerged was as strange as the effect itself. The velocity change seemed to depend on the spacecraft's direction. When a probe approached Earth from the south and flew out toward the north, it gained a tiny bit of extra speed. When it followed other paths, the effect was different or absent. This directional clue points a finger at Earth's own rotation, suggesting the planet's spin might be creating a subtle, unaccounted-for drag or frame-dragging effect on the surrounding space-time. But how some scientists have searched for conventional culprits, could atmospheric drag, tides, or even the pressure of solar radiation explain the nudge? The calculations say no, the effect is too large for these known forces. Others have looked toward more exotic solutions. Perhaps this is a hint that Einstein's theory of general relativity needs a tiny adjustment in how it handles rotating frames of reference. Or maybe, and this is a far more speculative idea, the spacecraft are brushing through a halo of dark matter particles trapped by Earth's gravity, exchanging a minuscule amount of momentum. The core of the problem is its scale. A few millimeters per second is agonizingly difficult to measure and model with absolute certainty across millions of miles. It sits in a frustrating gap, too large to ignore, yet too small to be easily diagnosed. Future missions equipped with more advanced atomic clocks and laser-ranging systems might finally capture this phantom in the act, pinning down its cause. Until then, the Flyby anomaly remains a testament to the fact that even in our own celestial backyard, gravity may still have a secret or two left to share. These subtle navigational ghosts are one thing, but the cosmos also produces explosions of such pure, unadulterated power that they threaten to tear reality itself apart. Out in the depths of space, a single flash can outshine half a universe. Fast radio bursts are cosmic screams, brief blasts of radio waves that last for just milliseconds. Yet in that sliver of time, they release more energy than our sun does over 80 years. These are not gentle signals, they are titanic explosions of pure force, traveling for billions of years across intergalactic space, only to be captured for a fleeting moment by our most sensitive dishes. Their discovery was almost an accident, buried in the archival data from the Parkes radio telescope in Australia, a tiny blip from 2001 that a sharp-eyed student, Duncan Lorimer, noticed in 2007. That one anomaly opened an entirely new field of astronomy, one dedicated to hunting the most transient and powerful signals in the cosmos. For years, the central mystery was repetition. Most fast radio bursts are one-off events, a single, spectacular flash and then eternal silence. But one source named FRB 1211-2 broke all the rules. It crackled to life again and again, firing off bursts in an unpredictable but undeniable pattern. This repetition was the key that finally allowed astronomers to pinpoint its home, a tiny, turbulent dwarf galaxy over 3 billion light-years away. The fact that it could repeat ruled out any model involving the total destruction of the source, like a collision between two neutron stars. Then, in April 2020, a magnetar within our own Milky Way galaxy, a highly magnetized spinning stellar corpse, erupted with a radio burst that was unmistakably a fast radio burst. For the first time, we had a confirmed culprit in our own backyard. A magnetar's magnetic field is so unimaginably powerful that a starquake on its surface, a snapping of its crust, can unleash a firestorm of radiation. But this solved one mystery only to deepen another. While we now know magnetars can produce some of these bursts, the energies of the most distant FRBs are so colossal that they strain even the most extreme magnetar models to their breaking point. What natural engine can possibly be this powerful? Theorists have proposed a menagerie of possibilities. Perhaps it is the violent birth of a black hole from a collapsing supernova, or the final, dying pulse from an evaporating primordial black hole. Some have even considered the possibility of cosmic strings, hypothetical defects in the fabric of spacetime, vibrating like unimaginably taut guitar strings. The sheer diversity of the bursts now being discovered by new facilities like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, which finds them by the dozen, suggests we are not dealing with a single cause, but a whole zoo of cosmic catastrophes. Each new detection paints a stranger picture, with some bursts showing intricate substructure, as if the signal itself is encoded with the complex physics of its birth. Could some of these bursts be the result of advanced technology, a byproduct of immense light sails powering interstellar vessels across the galaxy? While this is the least likely explanation, the sheer extremity of the phenomenon forces us to question all our assumptions. What other transient, fleeting events are flashing in the darkness, waiting for our instruments to become quick enough and our minds open enough to see them? The sheer violence of a gamma-ray burst is almost beyond human comprehension. In the span of a few seconds, a single one can release more energy than our Sun will emit across its entire 10 billion-year lifespan. These are the most powerful explosions to occur in the universe since the Big Bang itself, and we stumbled upon them entirely by accident. In the 1960s, American military satellites designed to monitor for secret nuclear weapons tests began picking up strange, intense flashes of gamma radiation that were clearly not coming from Earth. They were cosmic in origin, brief and utterly mysterious. For decades, their true nature was one of astronomy's greatest secrets. We now know these bursts come in two distinct flavors, each pointing to a different kind of cosmic catastrophe. Long gamma-ray bursts lasting more than 2 seconds are now linked to the death of massive stars in supernova explosions, specifically a type that creates a rapidly spinning black hole. Short bursts lasting less than 2 seconds are thought to arise from the even more violent merger of two neutron stars, the ultra-dense corpses of dead suns. A monumental breakthrough came in August 2017. Observatories around the world detected a short gamma-ray burst, designated GRB 170817A. At virtually the same instant, gravitational wave detectors felt the ripples in spacetime from the same event, the collision of two neutron stars over 100 million light-years away. This was the first ever multi-messenger observation of a single cosmic event, confirming beyond doubt that neutron star mergers are indeed a source of these brilliant flashes. Yet for every mystery solved, new, deeper questions emerge. We know these events create the bursts, but what is the precise engine that accelerates particles to within a fraction of the speed of light, forging jets of plasma that are narrower and more focused than any laser beam? How can a stellar collapse or a merger produce such perfectly collimated, relativistic outflows that tear across interstellar space? The composition of these jets remains a major puzzle, a soup of electrons, positrons, and magnetic fields whose precise recipe we are still trying to decipher. And then there are the truly bizarre outliers, the ultra-long gamma-ray bursts that shine for thousands of seconds, sometimes even for hours. What kind of stellar death throes could possibly sustain such an immense release of energy for that long? Could they be from the collapse of supergiant stars far more massive than any we have seen nearby, or perhaps from entirely new types of events we have not yet imagined? Space telescopes like Swift and Fermi continuously scan the skies for these sudden, devastating flares, each new detection adding a piece to a puzzle that is fundamentally about the most extreme physics the universe can produce. How do matter and energy behave under conditions of gravity and density so intense that the very rules of nuclear physics are rewritten? The quest to understand these cosmic cataclysms pushes our knowledge to the absolute limit, forcing us to look past the initial flash to the lingering, high-energy afterglow they leave behind. A single, powerful whisper from the cosmos arrived on a late summer night in 1977. For 72 seconds, the Big Ear radio telescope in Ohio recorded a signal so perfect, so precisely what scientists were listening for, that it seemed to defy chance. The signal was narrowband, focused on the hydrogen line frequency of 1420 MHz, a quiet channel in the cosmic radio din that many have suggested would be an ideal calling card for any advanced civilization trying to make contact. Its intensity rose and fell in a perfect curve, exactly matching the profile of a fixed celestial source drifting through the telescope's field of view as the Earth turned. When astronomer Jerry Amon saw the data printout, he was so stunned he circled the alphanumeric sequence and scribbled one word in the margin: "Wow." That single exclamatory note gave the signal its name and its legend. The search for an explanation began immediately, but the signal never returned. Decades of follow-up observations, using far more sensitive equipment, have scanned the same patch of sky in the constellation Sagittarius and found only silence. This one-time event eliminates most conventional explanations. It was not a passing airplane or satellite, it was not a military transmission, and it was not a technical glitch within the telescope itself. The signal's unique properties point to a source beyond our solar system. Some have proposed more mundane astronomical origins, suggesting it could have been emission from a passing comet, though the comets proposed were not in the right part of the sky at that time, and no other comet has ever produced such a powerful, focused signal. Others wonder if it was an incredibly rare and fleeting natural event, a type of stellar flare or a radio burst from a previously unknown celestial object that has simply never been seen again. The very brevity of the WOW signal is what makes it so tantalizing and so frustrating. With only one data point, it sits in a statistical limbo, impossible to verify and impossible to fully dismiss. It is a ghost in the vast archive of cosmic noise, a 1 in a billion anomaly that forces us to confront the ultimate question. Was this our first fleeting, unknowing contact with another intelligence, a beacon that flashed for a moment in the dark and then was gone, leaving us forever to wonder if we were ever truly seen? This singular event, a solitary question mark etched into a data sheet, connects to a broader, more persistent enigma, a sound that seems to emanate from the void itself. A perfectly orchestrated experiment in orbit can reveal physics we never knew to look for. This was the promise and the puzzle of the tethered satellite system, a bold mission where the space shuttle would deploy a satellite on a 20-kilometer-long conducting tether. The principle was elegant. As the tether cut through Earth's magnetic field, it would act like a giant dynamo, generating an electrical current that could be studied and even harnessed. But during the TSS-1R mission in 1996, the experiment delivered far more than anyone bargained for. As the satellite unreeled into the void, the tether began generating a current vastly stronger than any model had predicted. It was as if they had plugged a household appliance into a wall socket and received the output of a major power plant. The forces involved became chaotic and unpredictable, and then catastrophe. The overtaxed tether snapped, sending the $500 million satellite spinning away into a permanent orbit of its own. The immediate cause was a suspected electrical arc, a violent discharge that melted through the cable. Yet the deeper mystery remained. Why was the current so powerful in the first place? Our understanding of plasma physics, the behavior of charged particles in space, seemed to be missing a crucial chapter. The tether was essentially a giant wire moving through a magnetic field, and theory said it should collect electrons from the surrounding ionosphere at a certain rate. But the reality was a deluge. Subsequent investigations pointed to complex, non-ideal conditions. Perhaps the tether's own voltage created a large, enhanced region around it, a virtual antenna that collected electrons far more efficiently than a simple wire ever could. Maybe surface imperfections or unexpected interactions with the oxygen plasma created unforeseen electrical pathways. While these explanations have placated some scientists, a nagging sense of an unresolved anomaly persists for others. The forces acting on the tether exhibited dynamical quirks that pure electrodynamics did not fully account for. This was not just an engineering failure. It was a fundamental physics experiment that told us our textbooks are incomplete. The incident stands as a stark lesson that the space environment is a laboratory with variables we are still learning to measure. What other electromagnetic secrets are hidden in the gentle flow of plasma around our planet? Secrets that could only be uncovered by another such grand, and perhaps risky, structure extending into the void. This strange behavior of charged particles in orbit finds a parallel in the quest to understand the most elusive travelers of all, particles that seem to defy the very speed limit of the cosmos. The particles raining down on our planet carry energies that dwarf anything our most powerful colliders can produce. These are ultra-high energy cosmic rays, atomic nuclei traveling at almost the speed of light, each one a microscopic speck possessing the kinetic energy of a well-thrown baseball. According to a firm prediction made in the 1960s by physicists Greisen, Zatsepin, and Kuzmin, such particles should have a very short cosmic leash. Their theory, the GZK Cutoff, states that any cosmic ray with an energy above about 5 times 10 to the 19 electron volts should not be able to travel very far through space. Why? Because the universe is not empty. It is filled with the faint afterglow of the Big Bang, the cosmic microwave background radiation. A proton traveling at such a ridiculous speed would see these gentle background photons blue-shifted into a wall of intense gamma rays. The resulting collisions would produce a shower of new particles called pions, sapping the cosmic ray's energy over a relatively short distance. The calculation is clear. No cosmic ray above this energy threshold should be able to reach us from a source farther than about 160 million light-years away. This distance is our GZK horizon. Yet, when giant observatories like the Pierre Auger Observatory in Argentina look up, they see them anyway. These detectors do not catch the particles directly, but instead observe the immense cascades of secondary particles they create in the atmosphere, enormous air showers that span kilometers. The data is undeniable. Particles are arriving from beyond the theoretical horizon, carrying energies that by all rights should have been stripped away during their billion light-year journey. It is as if a marathon runner sprinted the entire distance without ever stopping for water, arriving as fresh as when they started. This is the GZK Cutoff Conundrum, a direct challenge to our understanding of both particle physics and cosmic geography. So how are they doing it? One possibility is that our maps are wrong, and there are incredibly powerful, unknown sources of cosmic rays lurking just within our local cosmic neighborhood, within that 160 million light-year bubble. But when we trace the arrival directions of these ultra-high energy events, they often point back to empty voids, regions of space with no obvious galaxies or cataclysms to explain them. Another, more radical idea is that our understanding of physics itself needs an update at these extreme energies. Perhaps Lorentz invariance, a cornerstone of Einstein's special relativity, is subtly violated, changing the rules of how particles interact with the photon sea. Or maybe these are not particles accelerated by distant black holes, but are instead the decay products of something far more exotic. Top-down models propose that super-heavy dark matter particles, relics from the universe's first instant, are decaying and releasing their immense mass energy directly into these ultra-high energy cosmic rays. Each detection is a message from the most violent processes in the universe, written in a code we have not yet broken. How do these cosmic bullets pierce through a universe that should be their shield? Unlocking their secret may require us to rewrite the rules that govern reality itself at its most extreme. Deep within the heart of our own galaxy, a strange and persistent light refuses to be explained. The center of the Milky Way should be a place of known chaos, dominated by a supermassive black hole and crowded with ancient stars. Yet data from the Fermi Gamma Ray Space Telescope has revealed an unexpected glow, a broad excess of gamma radiation that spills out for thousands of light years. This is not the sharp, pinpoint emission of a single pulsar or the predictable wash from cosmic rays slamming into gas clouds. This is a diffuse, energetic hum, strongest at the very core and fading outward, with a distinct spectral peak between 1 and 3 giga-electron-volts. It is as if you were listening to an orchestra and heard a powerful, steady note that no instrument on stage was playing. The discovery, first solidly identified around 2009, immediately set off a hunt for its source. The most thrilling possibility is that we are seeing the indirect signature of dark matter. In this scenario, clouds of weakly interacting massive particles, or WIMP, are concentrated at the galactic center. When two of these particles collide, they could annihilate each other, transforming their mass directly into energy and producing the very gamma ray excess we observe. The precise energy of the glow points to a WIMP with a mass around 30 to 40 times that of a proton, a tantalizing hint that feels almost too perfect. But science demands we exhaust the ordinary before embracing the extraordinary. Could this light come from a vast collection of unresolved millisecond pulsars? These are rapidly spinning neutron stars that act like cosmic lighthouses, and they do emit gamma rays. The problem is their distribution. To account for the excess, there would need to be tens of thousands of them clustered in the galactic center, a population far denser than our current models of stellar evolution predict. Other astronomers point to past outbursts from the central black hole, which could have accelerated cosmic rays that are now interacting with gas to produce the glow. Yet the spatial shape of the emission, smooth and extended, does not perfectly match the clumpy distribution of interstellar gas. The debate continues, with each new analysis of the Fermi data sharpening the mystery. The answer lies in the details. If the glow is truly from dark matter annihilation, it should be perfectly smooth, tracing the invisible halo of matter. If it is from pulsars, future telescopes with higher resolution should eventually be able to resolve the faint, individual points of light within the glow. We are in a waiting game, a standoff between a revolutionary discovery and a more complex but conventional astrophysical reality. This unresolved signal from our galactic core serves as a constant reminder that even our own cosmic backyard holds profound secrets, challenging us to look closer at the familiar and see the extraordinary hidden within. Our own planet holds a climate secret from the distant past. Billions of years ago, our sun was a much weaker star, shining with only about 70% of its current brightness. By every logical climate model, that reduced energy should have left the entire Earth a frozen ball of ice, a global snowball with no possibility for liquid water or the emergence of life. Yet the geological record tells a different story entirely. Ancient rocks, some over 4 billion years old, bear the unmistakable scars of flowing water and sedimentary deposits that could only have formed in a warm, wet world. This is the faint young sun paradox, a contradiction first clearly identified by Carl Sagan and George Mullen in 1972. How could a planet with a dimmer sun avoid freezing solid? The answer forces us to rethink the very nature of planetary atmospheres and their evolution. The most widely accepted solution lies in a vastly different air. Earth's primordial atmosphere was likely a thick blanket of powerful greenhouse gases, with carbon dioxide concentrations possibly hundreds of times higher than they are today. Methane, another potent greenhouse gas, could have been released in enormous quantities by early microbial life. Together, these gases would have acted like an insulating jacket, trapping the sun's feeble heat with remarkable efficiency and keeping the global temperature well above freezing. But the gas composition may not be the entire story. Perhaps the young Earth itself was simply darker, with a lower albedo, meaning it absorbed more of the sun's precious light. A surface with less reflective ice and more dark volcanic rock, or even an ocean with a different color due to chemical composition, could have soaked up just enough extra warmth. The behavior of clouds is another critical variable. Some climate models suggest that different cloud patterns in the past could have provided a net warming effect, rather than the cooling they often cause today. This paradox is far more than a historical curiosity. It reshapes our search for life beyond our solar system. When we calculate the habitable zone around other stars, the region where liquid water can exist, we must now consider that a planet's own atmosphere can dramatically extend those boundaries. A world orbiting a dim star might not be a frozen wasteland if it possesses a robust greenhouse effect, just as early Earth did. The resolution to this ancient mystery teaches us that life is not a passive passenger on a planet, but an active participant in shaping its own environment. The geological evidence proves our world found a way to stay warm against the odds, a delicate balancing act that allowed life to take its first tentative steps. What other atmospheric tricks might planets use to cheat the cosmic cold? Some of the largest planets we have found defy the very models built to explain them. Orbiting perilously close to their host stars, these so-called hot Jupiters bask in intense stellar radiation, yet they possess a curious trait. Their physical sizes are consistently, systematically larger than they should be. Standard models of planetary evolution, which carefully account for the intense heat these worlds receive, predict a certain radius for a planet of a given mass and age. But for many hot Jupiters, the reality is different. They are inflated, bloated to sizes 10 or even 20% larger than theory allows. It is as if you baked two identical cakes for the same amount of time, but one of them swelled up far beyond its pan for no apparent reason. This is the radius anomaly, a persistent gap in our understanding of planetary structure. The intense stellar radiation these planets receive should heat and expand their outer atmospheres, but our calculations suggest this alone is not enough to explain the observed puffiness. Something else must be pumping energy into their interiors, preventing them from cooling and contracting to their expected size over billions of years. One compelling idea is tidal heating. The gravitational pull from the nearby star could stretch and squeeze the planet's interior in a constant, friction-generating dance, much like repeatedly kneading a ball of clay until it grows warm. This internal heat would keep the planet inflated from the inside out. Another possibility lies in the planet's own atmospheres. Perhaps they are far more opaque than we assume, trapping heat so efficiently that it cannot easily escape, causing the entire world to remain swollen. Or maybe the process of planetary differentiation, where heavier elements sink to the core and lighter ones rise, is still ongoing, releasing gravitational energy that heats the interior like a slow-burning engine. Each proposed solution carries its own implications. Tidal heating would require a specific, non-circular orbit, which not all hot Jupiters have. Enhanced atmospheric opacity would force us to rewrite our models of how starlight interacts with alien air. The challenge is that we are trying to diagnose the internal workings of a world from hundreds of light years away, using only the subtle dimming of its star as it transits. This anomaly is more than a technicality. It signifies missing physics in our understanding of how giant planets work. If we cannot explain why a planet is the size it is, how can we truly claim to understand its composition, its history, or its fate? The inflated nature of these scorching giants forces us to look at other planetary oddities, to worlds where the rules seem not just bent, but completely rewritten. A star known as KIC 8462852 behaves like no other. Its light does not pulse with a steady rhythm or dip gently as planets pass by. Instead, it flickers and fades in wild, unpredictable plunges, with its brightness sometimes dropping by an astonishing 22%. This is not the subtle shadow of a Jupiter-sized world. This is as if a swarm of objects with a combined area far larger than the star itself were drifting in front of it, blocking its light in a chaotic, inexplicable dance. The star, nicknamed Tabby's star after its discoverer Tabetha Boyajian, was first flagged by citizen scientists sifting through data from NASA Kepler telescope, a mission designed to find other worlds by spotting the telltale dimming of their host stars. But this was something else entirely. No natural phenomenon we know of, not the pulsing of a variable star, not the trail of a disintegrating comet, not even a vast cloud of interstellar dust, perfectly explains the sheer depth and irregularity of these dimming events. The patterns are bizarre, with dips lasting for days and sometimes weeks with no clear periodicity. It is as if you were watching a street lamp at night and it suddenly, dramatically, grew dimmer for no reason you could see, only to slowly recover, and then do it again in a completely different way months or years later. This profound strangeness forced astronomers to consider every possibility, including the most extraordinary. Could we be witnessing the construction of a vast, alien megastructure? The concept, first proposed by physicist Freeman Dyson, imagines a civilization so advanced it builds a swarm of collectors around its star to harness nearly all of its energy output, a Dyson sphere. Such a structure, even if only partially complete, would block starlight in exactly the kind of random, deep, and irregular way we observe. While this remains the least likely explanation, its mere plausibility in the face of the data sent a jolt through the scientific community and the public imagination. The hunt for a natural cause intensified. Subsequent observations revealed that the star dims more at some wavelengths of light than others, a strong clue that whatever is blocking the light is not solid, but is likely composed of fine dust particles. This points away from solid megastructures and toward a more natural, if still bizarre, origin. Perhaps a giant, shattered planet or a family of countless comets, stirred up by a gravitational disturbance, is creating a vast, clumpy debris field orbiting the star. But what event could have created such an immense and chaotic cloud? Or maybe we are seeing the aftermath of a colossal planetary collision, the dusty wreckage still settling into a new system. The mystery of Tabby's star is a masterclass in how science confronts the unknown. It teaches us that when we push our observations to new limits, we will find things that defy our current categories, phenomena that sit at the very edge of our understanding. The star continues to be monitored, its every flicker analyzed as we slowly close in on an answer that is almost certainly natural, yet no less wondrous for it. What other cosmic oddities are waiting in our data, masquerading as magic until we learn to see them clearly? The first known visitor from another star system arrived without a trace. In October 2017, astronomers spotted a faint point of light moving at incredible speed, an object they named Oumuamua, Hawaiian for scout. Its trajectory was hyperbolic, meaning it was not bound by the sun's gravity and was just passing through our solar system on a one-way journey from the depths of interstellar space. This alone was a monumental discovery, but the real mystery began as it departed. Precise tracking revealed Oumuamua was not following a purely gravitational path. A slight but undeniable acceleration was pushing it, an extra nudge that grew more pronounced as it sped away from the sun. This is the kind of behavior we expect from comets, as sunlight vaporizes their icy surfaces, creating jets of gas that act like tiny thrusters. Yet Oumuamua displayed none of the classic signs of a comet. It had no visible coma, the fuzzy envelope of gas and dust, and no detectable tail streaming behind it. It was a dark, silent, and strangely accelerating rock. So what invisible engine was at work? The leading natural explanation points to outgassing from exotic ices. As the object swung near the sun, heat could have caused frozen hydrogen or nitrogen hidden just beneath its surface to turn directly into gas, a process called sublimation. This gas, venting into space, would provide the gentle push needed for the acceleration, all without producing the large amounts of dust that create a visible coma. The challenge is that a hydrogen iceberg would sublimate too quickly in interstellar space to survive its long journey, while a nitrogen iceberg, like a chunk from a Pluto-like world, would need to be unusually thick to account for the force observed. Each potential explanation comes with its own set of theoretical hurdles, a puzzle of composition and scale that remains unsolved. The object's other oddities only deepen the intrigue. Radar observations suggested it was highly elongated, perhaps 10 times longer than it was wide, tumbling through space like a cosmic cigar. Its brightness also varied dramatically as it spun, further hinting at this bizarre shape. The combination of its form, its tumbling motion, and its mysterious acceleration forced scientists to consider every possibility, even those that push the boundaries of known physics. While the vast majority of astronomers favor a natural origin, the sheer uniqueness of Oumuamua serves as a powerful reminder of how much we have yet to learn about the building blocks of planetary systems around other stars. Was this a fragment from a shattered alien world, a shard of nitrogen ice from the outskirts of a distant solar system, or something even stranger, future telescopes like the Vera see? Rubin Observatory are expected to find many more of these interstellar nomads. By comparing Oumuamua to its cousins, we will finally learn if it was a rare oddity or a standard piece of galactic debris. Its silent, accelerating departure leaves us with a fundamental question about the nature of the stuff between the stars. This mystery of a lone wanderer connects to the strange behavior of far smaller objects that have been with us all along. Even the silent face of our moon holds secrets that flicker in the darkness. For centuries, astronomers have documented strange, fleeting lights and color changes on its surface, brief anomalies known as transient lunar phenomena. These are not tricks of the atmosphere or illusions, but localized glows, sudden brightenings, and patches of obscurity that appear and vanish on the barren landscape, sometimes lasting for just a few minutes, other times for hours. Renowned observers like William Herschel in the 1700s reported seeing these mysterious lights, and in the 1960s, NASA even created a formal catalog of these events to prepare for the Apollo landings. The credibility of these sightings was profoundly bolstered when the astronauts themselves witnessed them. From lunar orbit, the crew of Apollo 11 reported a bright patch inside the crater Aristarchus, and the Apollo 12 crew saw a brilliant glow that they initially mistook for a light from their own spacecraft. These were trained observers right there, confirming that the moon was not entirely dead. So what could possibly be causing these flashes on an airless, seemingly inert world? The most straightforward explanation is meteorite impacts. The moon has no atmosphere to burn up incoming space rocks, so even small impacts would create a brief, brilliant flash of light as they vaporize on contact with the surface. Automated monitoring programs have indeed captured thousands of these impact flashes, yet this cannot account for the longer-lasting glows or the subtle color changes that have been reported. Another strong candidate is outgassing. The moon's interior may still hold trapped radioactive elements that slowly decay, releasing pockets of gas like radon. When these gases escape into the vacuum, they could disturb the fine lunar dust, causing it to become temporarily electrostatically charged and glow, or creating a faint, shimmering haze that obscures the terrain below. Some events might be explained by solar phenomena, where charged particles from the sun strike the lunar soil, triggering a form of light emission. But no single theory cleanly explains the full menagerie of reported events. Why do some glows appear red while others are white or blue? Why do they seem to recur in specific locations, like the craters Aristarchus and Plato? Modern efforts are using Earth-based telescopes and lunar orbiters to monitor the moon with unprecedented sensitivity, searching for correlations between these visual flashes and other data, like moonquakes detected by seismometers left by the Apollo missions. If a light flash coincides with a deep moonquake, it would be a powerful clue that internal processes are at work. The enduring mystery of these lunar flickers forces us to reconsider what we mean by a dead world. It suggests that even the most familiar celestial body in our sky may harbor a subtle, ongoing geology, a quiet activity that occasionally betrays itself in a fleeting, enigmatic glow. One final phenomenon stands as a monument to order within chaos. At Saturn's North Pole, a colossal hexagon of clouds, wider than our entire planet, has maintained its perfect geometric shape for decades. This is not a fleeting atmospheric fluke, but a permanent feature etched into the planet's very atmosphere, a six-sided jet stream spinning in a precise dance. When the Voyager probes first glimpsed it in the 1980s, scientists were stunned. The Cassini mission later confirmed it was not an illusion, but a towering structure spanning 30,000 kilometers across, with walls of cloud that plunge hundreds of kilometers deep into the gaseous abyss. It rotates with a period of about 10 hours and 39 minutes, matching the planet's own radio emissions, yet it remains locked in place, a stationary storm of impossible geometry. Why does nature, which so often favors spirals and ovals, choose a perfect hexagon on such a monstrous scale? The answer appears to lie in the physics of spinning fluids. In laboratory experiments, when a fluid is rotated at different speeds at its center and its outer edge, it can spontaneously form polygonal shapes. A hexagonal pattern emerges naturally under the right conditions, a product of shear and turbulence. This suggests that deep beneath Saturn's colorful cloud tops, a vast rotating current is shearing against the surrounding atmosphere, carving out this stable geometric form. Yet the laboratory models only take us so far. They struggle to explain the hexagon's extraordinary longevity and resilience. Saturn has endured long seasonal cycles since its discovery, with its north pole moving from winter darkness into sunlight. Yet the hexagon has persisted unbroken, its shape and rotation rate unwavering amidst the planet's immense atmospheric turbulence. What specific mechanism provides this profound stability, preventing the six-sided jet stream from dissolving into the chaos around it? Is there a deeper layer of the atmosphere, a hidden engine of stability that anchors this pattern in place? The Saturn hexagon is a breathtaking example of how simple physical laws can generate breathtaking complexity, a natural sculpture that challenges our intuition about how planetary atmospheres behave. As our journey through these 23 cosmic puzzles comes to a close, we are left not with final answers, but with a profound sense of wonder. Each mystery, from the ghostly pull of dark matter to this geometric storm on a gas giant, represents a frontier of human understanding. They are reminders that the universe is far stranger, more beautiful, and more mysterious than we have yet dared to dream. Each of these 23 cosmic riddles is far more than a simple gap on a map. They are tremors felt across the entire structure of modern physics, signaling that our foundation may be built on something we do not yet comprehend. Every unexplained acceleration, every missing particle, every impossible geometry is a potential portal, a crack in the wall through which we might glimpse an entirely new set of rules. History offers a powerful lesson. For decades, a tiny anomaly in Mercury's orbit defied Newtonian gravity. It was a small puzzle, a wobble that would not go away. That single, stubborn discrepancy became the crucial clue that led Einstein to his theory of general relativity, completely reshaping our concept of gravity. Today, we face not one but dozens of such anomalies, each one a potential Mercury. The patterns emerging from these diverse puzzles are impossible to ignore. The Hubble tension, the lithium problem, the ghostly pull of dark matter, they all whisper that our cosmological models, for all their stunning success, are incomplete. They are like a brilliant play where the actors are following a script, but the stage itself is made of a material we have never seen. The resolution will demand more than just sharper telescopes or bigger computers. It will require a conceptual leap, a fundamental rethinking of what space, time, and matter actually are. The next generation of observatories stands ready to guide that leap. The James Webb Space Telescope peers into the cosmic dawn, searching for the earliest galaxies to test our ideas of dark matter and inflation. The Vera Rubin Observatory will scan the entire sky, mapping the cosmic web in unprecedented detail to probe dark energy. And a new fleet of gravitational wave detectors will listen for the ripples from the universe's most violent events, potentially hearing the echoes of cosmic strings or other exotic phenomena. The most exciting possibility is that these mysteries are not isolated. Solving one could suddenly illuminate a whole cluster of others. Understanding the true nature of dark matter might unravel the secret of the missing antimatter. Pinpointing the cause of the Hubble tension could reveal a new property of dark energy. Each solution has the potential to create a cascade of understanding, a domino effect that reshapes our entire view of the cosmos. We are living in an era of profound transition, where the questions we are asking are preparing us for answers we cannot yet imagine. This grand tour of cosmic mysteries reveals a universe far richer and more complex than our textbooks could ever contain. These 23 puzzles are not signs of failure, but bright beacons illuminating the very edges of our understanding. Each unexplained acceleration and every missing particle represents a profound opportunity, a chance to tear down old assumptions and build a deeper, more truthful picture of reality. Science thrives not on final answers, but on the relentless pursuit of better questions, with each new discovery refining our